First, let's take a look at what we have. I have the source data open here in Data Inspector. The white areas are what we want to get rid of. But to know how to do that, we also want to look at the areas with valid data. If you zoom in very closely, you can see here that each individual pixel has three band values, red, green, and blue. And the different values mean how much of each is shown in each pixel. Let's go over to the areas now with no data. These are the white parts that we want to get rid of. Some of them are full white, meaning 255 for all bands, and some aren't, which means we can't just isolate one value and get rid of everything that has 255 for all bands. One thing to note, though, is that all the white areas have RGB values that are very close together. All right, now onto Workbench. I have here the completed workspace, and I'm going to step through the different portions to show everyone what's going on in each part of it. First, we will get rid of the images in the dataset that have no valid data in them. Since they are all close to white, the range of possible value in each image is quite small. One of the fastest ways to do this is to use the raster statistics calculator. This transformer calculates various statistical measures for bands in the raster. In this one, we will use band 0, which is red, and ask it to find the minimum. Images with real data will have a wide range of values, so we expect the minimum value to be at or close to 0, whereas tiles that are all white will have a value that's much closer to 255. If we inspect the data after it's gone through the transformer, there are some images that have a minimum value of 245, meaning that all pixels are close to or fully white. Next, we will use a tester to test for the images with minimum values of 245. Those that do are now taken out of our processing workflow. This did not, however, get rid of all the no data portions that are on images that do have valid data in them. And we want to isolate these areas, and one of the ways is to create a vector clipping mask, which we'll then use to cut out the white areas from the source data. To create this vector clipping mask, we first want to capture all the remaining white areas in the image. To do so, we'll generate a raster expression within the raster expression evaluator to find the extents of the areas where there are no data. In the transformer, we set the mode to one raster, referred to as raster A, and change the interpretation to an 8-bit unsigned integer band. Now, we'll go to the expression itself, which the transformer uses to calculate and reassign the values. We start with if, and then A0, meaning band 0 in the source raster, corresponding to red, is greater than or equals to 230, and A1, band 1, the green band, is greater than or equals to 230, and finally, A2, band 2, meaning blue, is greater than equals to 230, comma, 0, meaning then set the value to 0, comma, 1, meaning else set the value to 1. As all of the white areas in the images have very similar RGB values, and all of them are quite high, this expression will set values of all those areas to 0. Now let's look at the cache data. The fully black areas correspond with the white areas in the source data. There are also many dotted areas that are black in the portions that are supposed to have valid data, and we'll get rid of those later. But the reason they're there is that there's only so many colors that a raster can represent. And if we think about some rooftops, boats, or vehicles that might be colored white or really light gray, you can imagine some similarities in pixel values. Now, since we're only creating a clipping mask, we can get rid of them when doing the vector processing, but I just wanted to highlight it. Back to the output of the raster expression evaluator, there are only two values left, 0 and 1. Next, we'll use the raster band no data setter, setting a value of no data to 0 for the areas that we filtered using the raster expression evaluator. Looking at the result shows the outline of the new clipping mask, basically the areas where there are valid data. We'll use the extents of this to create a polygon clipping mask to clip the initial data set and generate our final area for the web map tiles. I will only go over the next portion briefly because it isn't the focus of this demo. We're essentially creating a polygon feature and cleaning it up by dissolving and using donut hole removers to get rid of the no data portions inside the polygon that we want to use to clip our data. I do want to draw your attention to the raster extents coarser, which creates a polygon based on the extents of the data present in the raster. So now let's take a look at the final clipping mask. We can take the source data and connect it to the clipper transformer as the candidate. and take the clipping mask and connect it to the clipper port of the clipper transformer. Inspecting the clipped output shows the data no longer has any white areas that have no data in it. We do have an issue though, because if we want to mosaic our data into a larger raster, the final output will be rectangular and there will be areas with no data in the final image. To deal with this, we want to add transparency via an alpha band. This alpha band will allow us to render the portions with no data in them fully transparent. To do this, we add the raster interpretation coercer and set the destination interpretation type to RGBA32. This means red, green, blue, alpha 32, 8 bits for each band. All the resulting pixels will have an alpha band, and an alpha value of 255 means that it's opaque. This is now ready to go into the mosaicer, as from here, no data areas will have an alpha value of 0, meaning that they will not show up in the final output. From here, it is extremely similar to the Flash demo. We import our various vector layers that are in MapInfo tab, GeoJSON, and shapefile formats, which is one of FME's strengths as it supports many different formats, style them in the MapNic rasterizer, and finally feed it into the WebMap tiler to create WebMap compatible tiles. Once all the tiles are completed, there is one more step that I want to showcase, and this is more for space optimization. If you remember, the tiling process creates many tiles at different sizes. Especially in the closer zoom levels, there is a high chance that there are some tiles that will have no data, in this case meaning having an alpha value of 0 or fully transparent. To save space, we don't want to write these out, so we'll use a similar procedure to earlier in the demo to find out where there isn't any data. This time, instead of using a red band, we are going to be using the alpha band. So I've added a raster statistics calculator here to find the maximum value of band 3, which is the alpha band. Inspecting the results shows us that there are some tiles that have a maximum alpha value of 0, meaning that they are fully transparent, and we're going to use a tester to sort them out of the data stream to ensure that we don't write them, and then feed the tiles that do have data into the test filter, and finally into the writer. The final output is essentially identical to the one from the Flash demo earlier, but slightly more space efficient as we have 1,766 fewer tiles being written out and read into the web page